Hello everyone, we're going to do a review of kinematics and vectors. In this review we're going to cover one-dimensional kinematics and 1D motion, vectors and operations with vectors, and I'm also going to include 2D motion because it's very closely related to 1D motion and vectors. So vectors are really important in physics because they extend the definition of numbers to include direction. So the numbers we are all used to are known as scalars. Scalar only has a magnitude or size, like the number 7. Number 7 is a scalar. However, a vector has both magnitude and direction. So a scalar value would probably be 5 kilometers, 10 miles, and any other measurement. However, a vector quantity would also include a direction. So a vector quantity would be 5 miles east. So here's some basic definitions. These two are key because all the other definitions are built off of these two. Displacement is defined as a change in position, and distance is defined as a length, the measure of how far you have traveled. So this little delta sign here, this is called delta, it's a triangle. So this is delta. Delta x basically means a change in x, x2 minus x1. So that's the form, like the very basic, the definition of displacement. So displacement versus distance. Displacement is a vector. It is an overall change in position. Displacement, I don't know if I mentioned, but displacement can also be negative, depending on whether you're moving back in position. So it's an overall change in position. Distance is a scalar quantity. It is the overall length traveled. So say at position A and position B, all right? But however, you take the blue dashed path. The length of that blue dashed path would be your distance. It's how far you've traveled. So that would be your distance. However, the overall change in position, this minus this length, the change in position, how far you're away, regardless of whatever crazy path you've took, that is displacement. Now we're going to move on to velocity versus speed. Now velocity is also a vector quantity, so velocity can be negative. An upward and rightward vector is usually positive. Forgot to include positive. It's usually positive. And a downward and leftward vector is usually negative. That is the convention. Right and up are positive, down and left are negative. It is the rate at which position changes over time. So speed, however, is a scalar. You don't need direction. If you put direction, it becomes a vector and you turn it into velocity. So speed is a scalar. So it's always positive. It is the rate at which distance changes over time. So here are two equations. We use V for both velocity and speed. We have delta x for displacement, delta d for distance, and delta t for time. So here's a practice problem. Usain Bolt's world record time for running 100 meters is 9.58 seconds. What is his average velocity? All right, so the way to do this problem is to substitute it directly into the formula for velocity, delta x over delta t. This results in 100 meters divided by 9.58 seconds, which is equal to 10.4 meters per second. To get a sense of how fast that is, in kilometers, it would be about 37 kilometers per hour. So about the speed of a car just traveling down a neighborhood road. All right, so we're going to start analyzing motion graphs. So we're going to start with position time graphs. Analyzing these position time graphs helps us understand velocity much better and helps us get better at analyzing graphs in general. graphs are a really important tool in physics. So we're going to start analyzing our first type of graph, position versus time. The position is on the y-axis and the time is on the x-axis. So if you actually look at the formula for velocity, v equals delta x over delta t, you can guess that the velocity of the object at a point in time, the instantaneous velocity, is given by the slope of the graph at that point. If you don't remember the slope formula, here it is. Right? So basically, what this means is this delta, it's x2 minus x1. This delta also means t2 minus t1. So if you take that into account, this looks suspiciously like the slope formula, which I put right here, which means the velocity is also equal to the slope of the graph at this point. So here's a practice problem. So let's say we have a cat running across a sidewalk. A graph of its motion is plotted above. What time intervals is the cat not moving? What time interval is the cat moving the fastest, and what is this velocity? What is the cat's displacement after 40 seconds? What is the distance the cat traveled after 40 seconds? What time interval is the cat to the left of its original position? So we're going to assume that cat's moving left and right. So here are the answers. So I'm going to walk you through these answers. So for part A, is what interval or intervals is the cat not moving? So that's basically 10 to 15 seconds. If you remember, a straight horizontal line has a slope of 0. And since in a position time graph, velocity is equal to the slope, that means velocity must equal 0, and the cat therefore cannot be moving. Letter B is what time interval is the cat moving the fastest, and what is this velocity? So if you look at all the times where the cat is moving, you can easily see that this interval is steeper. That means this interval has the highest slope and therefore has the highest velocity. So you can use the velocity formula, or you could just use a slope formula, and that'll give us 60 divided by 10, which equals 6 meters per second. So part C, what is the cat's displacement after 40 seconds? Well, that we could just use the definition of displacement is a change in position. So at 40 seconds, this cat is at negative 40 meters. 40 meters left of its original position, because remember, we said left is defined as negative. So negative 40 minus 0, that's its original position. It starts at 0. So negative 40 minus 0 will equal negative 40 meters. So that will be its displacement. So part D will tell us to find the distance from 0 to 40. Now, here's where people get confused. They will also say negative 40, but that is not correct. It's the total length this cat has traveled. So from 0 to 10, the cat goes 60 meters. So it travels 60 meters, so this is our first term. However, from 15 seconds to 40 seconds, it will go down to 100 meters. So 20, 40, 60, 80, and 100. So that's 100 meters. So if you were to add all that up, that will equal a total distance of 160 meters. So this is drastically different than displacement. Shows they're completely different concepts. And what time interval is the cat to the left of its original position? So left is negative, so we need to find the interval where the graph is below the x-axis. And that indicates a negative y value. In this case, will indicate a negative position, or left. So it starts going negative at 30 seconds, it will keep on going downward, and then it will go back up, so the cat will start to head right, and it will exit at, 60 seconds. 55 seconds. So this should be 55. So that's 55 seconds. So 30 to 55. So now we're going to analyze another type of graph, velocity time graphs. So analyzing a velocity time graph is slightly different than analyzing position time graphs. So the velocity time graph, the velocity is on the y-axis. So the velocity is on the vertical axis. There is a way you can find the displacement in a time interval. All right, I'm just going to put it on draw mode. Okay, so let's say you were traveling at a constant velocity v for some time t, okay? For some time delta t. So this is, to find the displacement, you rearrange the velocity equation v equals delta x divided by delta t for delta x. You should get delta x equals v delta t. So if velocity is constant, like in time interval 2 to 10 seconds, you can find the displacement using this equation. You get 8 meters per second times 8 seconds equals 64 meters. If you notice in the rectangle under the graph at time interval 2 to 10 seconds, it's also equal to 64. So to just get a sense of what that means, so this is, we said it is our time axis. So this will be some time delta t, which we already know is 10 seconds. 8 seconds. So this is delta t. So this is some random time interval, and this is a constant velocity. So if this is a constant velocity, then this is a rectangle, and the height of that rectangle is the constant velocity this object is traveling at. So that'll be v. So we know area is equal to length times width. So that's v times delta t. And we already see here, if we actually rearrange this equation, that just equals delta x. So the area under the graph during a specific time interval will equal to the displacement in that time interval. So I'm just going to let you grasp that in before I take everything off. All right, just take off. So in general, you can find the displacement traveled in a time interval if you find the area under the graph in that interval. By under, I mean the area between the graph and the x-axis, or in this case, the t-axis. So we're going to continue with our analysis. So in position time graphs, the slope of the graph at a point is the velocity. So furthermore, there should be something that represents the slope of the velocity time graph. And there is something, and this something is known as acceleration. So acceleration is the rate at which velocity changes over time. So when velocity is constant, acceleration is 0. So see how here the velocity is constant. It's always at 8. That means the slope is also 0. That means there's 0 acceleration. So acceleration has units of meters per second, or meters per second squared. So I'll just show you how this works. So this is meters per second. So if you're dividing by something, you're basically multiplying it by its reciprocal. So the reciprocal of second is 1 over second. All right, and if you multiply you multiply these two, you get meters. And second times second is second squared. So that's how we get this second notation. And this second notation is used more often. Meters per second squared. So let's move forward. So we have a practice problem here. A car is traveling along a straight road. Its velocity as a function of time is plotted above. What time intervals is the car moving with a constant speed? At what times is the car not moving? At what time intervals is the car speeding up? What time intervals is the car slowing down? What is the highest acceleration the car achieves? And what is the total displacement after the end of the journey at 18 seconds? So this is the end, 18 seconds. So part A is what time intervals is the car moving with a constant speed? So if the car is moving at a constant speed, then the slope of the graph at that point must be equal to 0 because it will just keep on staying at this particular y value, or in that case, the velocity. So we can see from this graph that is equal to 0 to 4 seconds. So that's the first time interval. And there's another one at 9 to 13 seconds where the car is not moving. Part B, at what time is the car not moving? Now remember, this is a velocity time graph, not a position time graph. So the 0 slope thing doesn't really do anything. So that just tells you whether the car is moving at a constant speed. It doesn't tell you whether it's not moving. However, you can find out whether it's not moving. How? Because if the velocity is 0, then the car is not moving at all. So a time at which velocity is equal to 0 will give you the time at which the car is not moving momentarily. And this time, 1 is equal to 6. So this is 6 seconds. And about goes down to 0 at 18 seconds. So I'll just say 18 seconds because it looks like it's at 0. At what time intervals is the car speeding up and slowing down? So the car is speeding up at this time interval, 6 to 9 seconds. 6 to 9 seconds. And you might think, wait a minute, the graph is upward. This graph is upward. Why is it not 4 to 6? Because if you think about it, if the car is moving left, this graph is approaching 0. That means the car is slowing down at that point. So it's slowing down at that point. And the car is slowing down 4 to 6 seconds. It also slows down. I didn't put this in, but it also slows down during the interval 13 to 18 seconds. So it's 4 to 6 seconds and 13 to 18 seconds. It will be slowing down. Now for part D, you can just find the acceleration using the slope to the highest acceleration the car achieves. It will be equal to this because this is steeper than this value right here. It looks a lot steep. Not a lot steeper, but it is steeper. So that will be 18 meters per second minus negative 12 meters per second. Remember, this is negative. Divided by 9 seconds minus 4 seconds equals 6 meters per second squared. What was the total displacement after the end of the journey at 18 seconds? Well, you just find the total area. So this is not under the graph, it's a bit over the graph, but by under you mean the area between the graph and the x-axis. So this area is a trapezoid. This area is also a trapezoid. However, this will be considered like a negative area. So this consider as a negative area, and then you add this area and this area together to get the total displacement. So that's what I did here. I wrote out the formulas. So 1/2 times height times base 1 plus base 2. And that gives us -12 meters per second times 6 seconds plus 4 seconds divided by 2 plus 18 meters per second times 6 seconds plus 18 seconds divided by 2. And if you add all that up, you get a total of 156 meters. So this is the equation form for acceleration. You might have already guessed that this is the equation because it's basically slope. Instead of y and x, you have v and t. So this is the equation form of acceleration. Oh, I didn't notice. Okay. So the kinematics equations. So these are a set of 4 equations that can be used to solve any motion problem. Well, if the acceleration is constant. These don't work if the acceleration is changing. You might be thinking that we forgot to do acceleration time graphs, but most likely the acceleration time graphs you receive are only horizontal lines, constant acceleration, just as these equations. So they're easier to analyze. So these are the 4 equations. Vf equals v naught plus acceleration a times delta t. Then you have this the second, third, and fourth equations. You'll be given these equations on a physics test. However, it's helpful if you know how these equations work. They can all be derived by the acceleration equation, the velocity equation, the definition of average velocity. So those together can help you derive all 4 of these equations. But I can't do them here. It would take too much time. So I'll just give you these 4. So here's a practice problem. So a train is chugging along with a velocity of 30 meters per second. The conductor sees a river full of alligators 200 meters away. So what is the minimum rate at which the train can slow down so the train can't hit the river? So it will help if you list out what you have first. Okay, so you have a initial velocity of 30 meters per second. You have a displacement of 200 meters per second. They don't give you a time, and they want you to stop. So the slow down so the train can't hit the river, that will only happen if you stop right before you hit the river. So final velocity is 0. So one more thing I need to point out is these equations are helpful because each of them is missing one of these variables. Initial velocity, final velocity, acceleration, time, and displacement. So if you find out what's missing and what you need to find, what you're given, you can use the correct equation. So we need to find acceleration. So we can automatically rule out the second one. We're not given time, so we should use the fourth one. So I have the fourth one right here. So I subtract v naught squared, then divide by 2 times delta x. That's vf squared minus v naught squared divided by 2 delta x. That equals 0 meters per second squared minus the quantity 30 meters per second squared divided by 2 times 200 meters equals this is negative 2.25 meters per second squared. So, and this is negative because you're trying to slow down. So if you're slowing down, the acceleration will be negative from a positive velocity. So now we're going to talk about free fall. An object is said to be in free fall if the only thing accelerating it is gravity. And freefall will ignore the effect of air resistance, but the kinematics equations can still be applied. The acceleration is a constant known as g, the acceleration due to gravity on Earth, E should be capitalized, which is approximately equal to 9.81 meters per second squared. However, in kinematics, we'll use the negative because downward is negative and signs matter. So as you can see, we're going to ignore air resistance. So these arrows represent the velocity. So this is like zero velocity. It's increasing. That's just g, the acceleration, accelerating this ball downward. And you can see the displacement, velocity, and acceleration graphs. Acceleration is negative 9.8. So the velocity, well, this is for an object being thrown up in the air, right? So if you have an object thrown up in the air, the velocity is initially positive because it's moving up. However, it starts to slow down. And it momentarily comes at rest, and then it falls back to the floor again. And the displacement graph is really simple. It goes up, stops right for a moment, and then starts to go back down. And please know, during freefall, the object is always accelerating. So if you throw a ball up in the air, it does momentarily come at rest, but that does not mean the object is not accelerating. It just means the object has no velocity, but still acceleration. Because the acceleration line is constant. This is just going down. It doesn't just stop. It will just keep on going more and more negative as the ball begins to fall down. So we have a practice problem right here. So you drop a rock from a 40-meter tall building. So part A, find the time the rock spends in the air. So part B, what is the velocity right before landing? And C, from what height should you drop this rock so it spends exactly 5 seconds in the air? So this might look intimidating. However, it's just application of the kinematics equations with the acceleration being replaced by g. So we have our first one. Why? Because we're given the displacement, 40. We're given the acceleration, that's just g. We're giving initial velocity, it's dropped. So it will start at 0. So we're given initial velocity, which is 0. So this term just goes out completely. So we're left is delta x equals a times delta t squared divided by 2. And you just solve for delta t, multiply each side by 2, and then divide by a. So I replaced a by g just to make it more clear. All right, keep in mind that delta x is negative. You're going downward. So you're lowering your position. So your displacement overall will be negative. And that works out because this is also negative, and in the real world, you cannot have a square root of a negative number. So it all works out. And they'll get you to about 2.86 seconds. Part B, what is the velocity right before landing? So we already know the time, so we know the initial velocity, which is 0, and that makes it really easy. It's because it's just substitution here. We don't even need to arrange anything. We have 0 meters per second plus negative 9.81 meters per second squared times 2.86 equals 28.01 meters per second. Okay, so for this, part C, from what height should you throw this rock so it spends exactly 5 seconds in the air? So delta x equals v naught delta t plus a t squared over 2, or 1/2 a t squared. All right, so v naught is 0. Our initial velocity is 0, so that just goes out. And we just plug in the values. We want exactly 5 seconds. So we plug in the values, negative 9.81 times 5 squared divided by 2. And that gives us about 122.63 meters. So that's the height you should throw if you want exactly 5 seconds in the air. So now we're going to move on more on vectors. You just introduced it very briefly. Now we're going to get more in depth with vectors and how vectors can be added and subtracted. It's not really hard adding and subtracting vectors. So to find the magnitude of vectors added in the same direction, keep in mind same direction or opposite direction, in one dimension, you can add their values together. So in this example, you have vector with facing right toward the right, that's 3, plus another vector facing towards the right, which is 7, equals a longer vector, which is 10. Basically common sense. And conversely, you have 10, a long rightward facing vector, plus a leftward facing vector, with value negative 3 equals 7. So just 10 plus negative 3, or 10 minus 3 equals 7. So if you want to draw what is known as the resultant vector, so for 1D, you just draw a vector in whatever direction, positive or negative, the vector is with the appropriate size. So we have 3 plus 7, so the overall answer, the magnitude is positive. So the answer is positive, that means you draw it towards the right and you draw it like larger than what is before. So 10 plus negative 3, well, the answer is still positive, but it should be smaller than this because this magnitude is smaller than this magnitude. So it'll be a bit smaller than before. However, if you have this crazy arrangement of vectors like this, two-dimensional vectors, so what you do is you start your vector at the end of the first vector, the tail of the first vector, and you end the vector on the tip of the last vector, this arrow-looking thing. So the red vectors are the result of adding the smaller colored ones. So let's do a problem. So add the vectors shown. So you have two sets of vectors, this set and this set. So for the top one, we have negative 3 plus negative 1 equals negative 4. All right. So we drew our blue resultant vector. So negative 3 plus negative 1, that will be negative 4. So it will face downward. And it will be like the size of it, the length of it, will be larger than either of these. So this will be our resultant. So for part B, negative 7 plus 5 equals negative 2. This is negative, so it faces towards the left. However, it should be a lot smaller because we took out this positive 5 from this red vector. So it should be much smaller than before. However, what about a situation like this? Add the two vectors. Now these are not in the same direction, so you can't really add these two vectors. It's not 6 plus 2. That's only for 1D vectors, the same exact direction. So not the same direction, but one dimension. So this right and left, right and right, left and left, that's when you can add. Or up and down, up and up, just one dimension. However, if you mix up and left or right and down, you can't add these. However, there is a way to add these two vectors. So if you want to add these two vectors, now this is the Pythagorean theorem. If you remember, a squared plus b squared equals c squared. So you apply the Pythagorean theorem because this is basically a right triangle. So 6 plus 2, no, sorry, not 6 plus 2. This is a squared plus b squared to c squared. You solve for c by taking the square root, the positive square root. Negative does not make sense here. You plug in the values, you get root 40 equals 2 root 10, which is about equal to 6.32. So this is the actual resultant vector. If you want to find a direction, you don't use northeast, you don't use northwest, you use an angle measurement, an angle above the horizontal. So what you do is, this is not exact, so you shouldn't use this value. So we're going to use the tangent ratio. So if you do SOHCAHTOA, TOA is opposite over adjacent. So that'll be 2 over 6. So tangent of theta. So this is theta, usually means angle, equals 2 over 6. I just simplified the fraction here. So theta equals the inverse tangent, or the arctangent of 1 over 3. So the inverse tangent equals 18.4 degrees. Now, here is something that will be really useful, especially later in physics and actually later this presentation, is the fact that a 2D vector, a vector with like a magnitude and a direction in the form of an angle, can be broken into components of x and y, so that when these components are added, they create the same vector A. So this is our vector A, right? We have AX and AY. AX is our x component, AY is our y component. So AX plus AY must equal A, and it will work out. Now, if you know the angle between the horizontal and the vector, you can use SOHCAHTOA and the trig ratios to find the other components. So AY is A sine theta, so sine theta is opposite over a hypotenuse, AY over A, you multiply each side by A, and that equals AY equals A times sine of theta. And this is the same exact thing for AX. You just do cosine, that is adjacent over hypotenuse, so that's AX over A. Then you multiply each side by A, you get AX equals A cosine theta. So here's a practice problem. Break this vector into its components. So I'm just going to assign a value A to equal 7. It will just help with the notation and actually writing it down. So sine theta will equal AY over A. So the vertical component over the actual magnitude of the vector. So if you arrange for AY, multiply by A, you get AY equals A sine theta, which is 7 times sine of 40 degrees, which is about equal to 4.50. Now cosine theta equals A sub x, or AX divided by A. You multiply each side by A, and you get AX equals A cosine theta, which equals 7 times the cosine of 40, equals 5.36. So now we're going to move on to 2D motion. And in this section, and this is our final section we're going to review for kinematics. In this section, we're going to see why this breaking into components thing is so important, and how we can solve motion problems beyond the first dimension. So here's an introduction to a 2D motion. 2D motion is almost the same as 1D motion. However, the velocity will not be directed in an angle, and there'll be 2 dimensions, an x dimension and y dimension. However, since velocity is a vector, you can break it up into components, Vx and Vy. So here's one important thing to know. The components are independent of each other. So the x component of velocity does not affect the y components, and the y components do not affect the x components. So how a projectile moves horizontally will not affect how it moves vertically. And this is sort of proof. This is like a ball launcher giving this ball, this yellow ball, some horizontal velocity and just shooting it across. And this is just like a claw type thing holding this ball up. And pretend these blue lines are like lasers or something that can detect when each ball has passed through it. An ordinary person might think, hey, the yellow ball is much more distance to travel, it will take slower. However, that's not true. The x component do not affect the y component. So the y component is being accelerated by gravity. So the acceleration of gravity is the same for both the pink and the yellow ball, since they're close to each other. And since air resistance is negligible, the only thing acting upon it is gravity, which means these two balls will pass through these bluish laser things at the exact same time, and they will land on the floor at the exact same time. Why? Just because it's shot out with a horizontal velocity doesn't mean the vertical velocity will be impacted. Now, we're going to try to solve a problem. Here are some tips. So first, break your velocity into components, x and y, using SOHCAHTOA and your trig ratios. So this is important because it lets you analyze both x and y. And then the second step is, based on a problem, use one of the 4 kinematics equations in either x or y. I would recommend solving for time for some problems, for most problems, because it's the only variable that remains the same for both x and y. There's no x time or y time because that's ridiculous. Time is the same for both x and y. Do not mix x and y. Anything that goes in x equation must be x. Anything that goes in the y equation must be y. You don't want to mix these two. You'll get a wrong answer. So x's stay in the x equation, y's stay in the y equation. Then you can use the answer you got in the first equation, and you can apply it to the other component, the x or y component, whichever one you have last, and you can find another unknown. And that way you can find all the unknowns. So here's a practice problem. You roll a ball at a velocity of 2 meters per second from a 1.5 meter table. Find A, the time the ball takes to reach the floor, B, distance from the table that the ball lands, and C, the velocity, magnitude, and direction of the ball just before hitting the floor. Okay, so let's see what we have. So V, not y, the initial y velocity. So this is our initial velocity in the first place. There is no initial y velocity. Y velocity is 0 at this point. It is only going horizontally. However, gravity will start to accelerate that y component more and more and more. So gravity will start to pull it down even more, increasing the y component, and therefore making it fall down to the floor, because the y component will start to increase from 0. Originally, it is 0. That's why it's horizontal. So v naught y is 0. So we're going to solve for time, because that's part A. So this problem basically guides you through the process. So since v naught y is 0, this term can get out. So you just have g times delta t squared divided by 2. I'll just use g in the y equations because that is usually the acceleration due to you'll face in a typical projectile motion problem. However, you can use a, y if you want. So you arrange this for delta t. So multiply by 2 and divide by g, then take the positive square root. Negative time does not exist. So you take the square root of 2 times negative 1.5, divide by negative 9.81. Remember, this displacement's negative. You're going down. So if you're going down, displacement must be negative. And again, it works out because g is negative. So you take the square root of this, you get about 0.55 seconds. So that's your time. Now, if you use the actual definition of velocity, delta x or delta t, then arrange for delta x. Now, one thing I want you to point out, this delta v, this horizontal velocity will stay constant. Why? Because the y component does not affect the x component. So Vx will stay constant because there is no acceleration happening at Vx. So Vx will stay constant. That means we can just sub in Vx of 2 meters per second times 0.55 seconds. And that will give you a total like 1.11 meters away from the base of the table. Right? So V sub y, so you might be asking where I got this from. This is just V equals V naught plus AT. However, V naught y is 0. So I just took that out beforehand. So we got V sub y equals G delta T. So that's just negative 9.81 meters per second squared times 0.55 seconds equals 5.42 meters per second. So we're done with part B. I didn't stop. So part B is 1.11 meters. So now we're working on part C. So where were we? Yes. So 5.42 meters per second. So that's just the Vy at this point. Right before it hits it, 0.55 seconds. Right before it hits it, this is the y velocity over here. However, that's only the y velocity. If you want to find the actual velocity of the ball, use Pythagorean theorem. Treat it as two vectors that you're trying to add together. So Vx squared plus Vy squared equals V squared. I just took the square root beforehand. So we got this. And that equals square root 2 meters per second squared plus 5.42 meters per second squared equals 5.78 meters per second. So we can use the tangent ratio of opposite over adjacent. So that's just the y component over the x component. So that's 5.42 divided by 2. We get an angle of 69.8 degrees, or about 70 degrees. So the velocity, magnitude of the direction of the ball just before hitting the floor will be 5.78 meters per second and 69.8 degrees below the horizontal because the Vy is negative. I forgot to put a negative sign here, but Vy is negative. Okay. Let you grasp that in. It's negative. This is negative. It's a negative angle. It's below the horizontal. And you can put a negative here if you want, because anything squared is positive, so it'll still work out. Okay. Onward. So let's go to this practice problem. This is a little harder, but it's not as hard if you understand how breaking things up into components work. So an explosive rock gets shot out of a 20-meter tall volcano, short volcano, with a velocity of 25 meters per second at a 35-degree angle. Find the distance the rock travels before landing and find its final velocity. So this V naught is at an angle, so it'll have an x component and a y component. This is why the component stuff is so important. Then I can just deal with x and y separately and use y, and you could use the values obtained from the y component to help you to get values that you can obtain from the x component, especially time. So I'm going to solve for the y and x and y components first. So that's just V naught sine theta. If you don't know where you got that, it just, sine theta is opposite over hypotenuse, so V naught y over V naught. Then you just multiply each side by V naught. So that's where you get that equation. Now, always write it like that because not much space, and it helps you save time. So 25 meters per, that equals 25 meters per second times the sine of 35, which equals 14.3 meters per second. And then we have V naught x equals V naught cosine theta equals 25 meters per second times cosine 35. That equals 20.5 meters per second. So we can use the kinematic equation without the final velocity. So that's V naught delta t plus a half at squared, or in this case g. However, we have an initial y velocity, so it will not be as simple. In fact, we get a nasty quadratic equation you'll have to solve. So if you do the mess, and it's an absolute mess of using the quadratic formula, and there's really no other way to do it, you'll get a time equal to about 3.95 seconds. All right, I don't want to show the quadratic formula work here because you might have already imagined with these numbers, it will be quite messy. So I just solved it beforehand and I got about 3.95 seconds. All right, so we have Vx equals delta x over delta t, and I solve for delta x, which is Vx delta t, so V naught x delta t. So we're going to use this value right here and sub it in right here. That's 20.5 times 3.95. That equals 80.85 meters. Okay, so that's how far away from the volcano that's how far away from the volcano this explosive rock is going to land. All right, so we're asked to find the final velocity, right? It's not much different than the last example. Just you have a V naught y, so you have to use a full formula over here. Vy equals V naught y plus g delta t, or a y delta t. That equals 14.3 meters per second plus negative 9.81 meters per second squared times 3.95. You get about negative 24.45 meters per second. I cannot stress the importance of the correct signs. I actually did that mistake while creating this. I had to fix it later. So you have to be very careful about the signs. Otherwise, you'll mess up your problem. So you just use the Pythagorean theorem. I already square rooted everything beforehand. So square root Vx squared plus Vy squared. Just square root of the quantity 20.5 meters per second squared plus the quantity negative 24.45 meters per second squared. That equals 31.9 meters per second. So that will get us tangent. That will get us a magnitude of 31.9 meters per second. Now again, you can use a tangent ratio if you want. You can use a sine ratio. I just prefer tangent equals Vy divided by Vx. That'll just give you a theta equal to the inverse tangent of Vy over Vx, which is the inverse tangent of negative 24.45 divided by 20.5, which is negative 50.02, or very close to negative 50 degrees. So this theta will be negative 50 degrees below the horizontal. All right, that's the end of our review. I have covered most of the topics. I might do a special video on deriving the actual kinematics equations. I don't know yet, and whether I'll actually do that or not, but it's this is the end of our review on kinematics. If you have any questions, just comment below. Thank you so much.